Imagine a car where the most important structural component isn't made of steel, no reinforced chassis, no rigid frame running beneath your feet, just a battery. Now that sounds wrong, almost dangerous, because for over a century, the automotive industry has been built on one unquestionable assumption, that a car needs a dedicated structure to survive. But what if that assumption is already outdated? What if the heaviest, strongest, and most expensive component in an electric vehicle is quietly replacing the chassis itself? And if that's true, then we are not just redesigning cars. We are redefining what a car actually is. And today, we are going to understand why. To understand why this idea feels so radical, we need to go back to the very beginning of the automobile. Because for more than a century, every car on the road has followed the same fundamental rule. A car is built around a structure, not the engine, not the fuel tank, the structure. In the early days of automotive engineering, this structure was brutally simple. A heavy steel ladder frame, two long beams running from front to rear, connected by cross members. The body was placed on top like furniture on a platform. This is what engineers call body-on-frame construction. It was strong, durable, and easy to repair. And even today, trucks still use it. But it had a problem: weight, too much of it. As cars became faster, more efficient, and more refined, engineers realized something uncomfortable. Carrying a separate frame meant carrying unnecessary mass. And in engineering, mass is never free. It affects everything: acceleration, fuel consumption, handling. So the industry evolved. By the mid-20th century, a new philosophy took over: the monocoque chassis. Instead of building a car on top of a frame, the body itself became the structure. Panels were no longer just cosmetic. They carried loads. They distributed forces. They absorbed impacts. The car became a single integrated shell, lighter, stiffer, more efficient. And for decades, this was the pinnacle of automotive design. Every component had a clearly defined role. The engine produced power. The fuel tank stored energy. The chassis carried the load. Simple, logical, proven. And then electric vehicles arrived. And quietly, they broke that logic. Because in an electric car, the most important component is no longer the engine. It is the battery. And this battery is not a small component hidden somewhere in the vehicle. It is massive. A modern electric vehicle carries a battery pack that can weigh anywhere between 400 to 700 kilograms. That is not a component. That is a structure. But here is where things become strange. Engineers did not redesign the car around the battery. Instead, they did something far more conservative. They built a protective box around the battery and then placed that box inside the chassis, which means something unusual happened. The car now carries two structures: a chassis and a battery enclosure. Both strong, both rigid, both heavy, both doing almost the same job. And this is the moment where the entire industry should have paused and asked a very simple question. Why? Why are we carrying two structural systems inside the same machine? Because once that question is asked, everything begins to change. This is where the story stops being historical and becomes uncomfortable. Because once you start looking at modern electric vehicles through an engineering lens, you begin to see a contradiction, a very expensive one. The physics problem. Cars are not static objects. They are constantly under stress. Every acceleration pushes the structure backward. Every braking event throws weight forward. Every corner twists the entire body. Engineers call these forces load paths, and managing these forces is everything. This leads to one of the most important concepts in automotive engineering: torsional rigidity. In simple terms, how resistant a car is to twisting. Imagine grabbing the front and rear of a vehicle and trying to twist them in opposite directions. If the structure flexes, everything suffers. Handling becomes vague. Ride quality deteriorates, noise increases, and in extreme cases, safety is compromised. So engineers have spent decades chasing one goal: make the structure stronger. But here's the problem. Strength comes with weight, and weight is the enemy of efficiency. This creates a fundamental engineering conflict. You want a car that is rigid, but also light, strong, but efficient. And for decades, the chassis was the answer, until electric vehicles complicated everything. The traditional EV architecture. In a combustion car, energy storage is simple. A fuel tank, lightweight, compact, passive. But in an electric vehicle, energy storage becomes the dominant element. A modern EV battery pack is enormous, not just in size, but in complexity. Inside that pack are thousands of lithium-ion cells. They require thermal management, structural protection, electrical isolation, crash resistance, and all of that is wrapped inside a rigid enclosure. A structure inside the car. But remember, the car already has a structure, the chassis. So now we have two layers: the chassis, designed to carry loads, the battery pack, designed to protect itself from loads, and both are reinforced, both are heavy, both are expensive. This is not elegant engineering, this is duplication. Imagine designing an airplane with two fuselages, one to carry passengers, another just to protect the first one. That's effectively what modern EV architecture looks like. And this is where the problem escalates. The weight spiral. Because this duplication creates something engineers fear the most: a feedback loop. The battery is heavy, so the chassis must be stronger to support it. But a stronger chassis is heavier, which means the vehicle becomes heavier, which means you need a larger battery to maintain range, which adds even more weight. This is known as the weight spiral, and it is brutally difficult to escape. Let's put this into perspective. A typical gasoline SUV might weigh around 1,700 kilograms. Its electric equivalent? Easily over 2,200 kilograms, half a ton heavier. That extra weight doesn't just affect efficiency, it changes everything. You need larger brakes, stronger suspension, reinforced structures, and every one of those adds even more mass. So now the car is not just heavy, it is structurally overbuilt to support its own inefficiency. And this leads to a deeper question, a dangerous one. If the battery is already the heaviest and one of the strongest components in the vehicle, why are we treating it like cargo? Why are we protecting it instead of using it? Because if the battery is already a rigid, reinforced structure, then perhaps the chassis is no longer necessary. And this is where the story takes a radical turn. This is where the industry stops asking how to protect the battery and starts asking a far more dangerous question. What if the battery doesn't need protection at all? What if it is the structure, the concept? The idea sounds deceptively simple. Instead of placing the battery inside the chassis, you make the battery part of the chassis itself, not cargo, not a component, a load-bearing element. In engineering terms, this is called a structural battery pack. The battery is no longer something the car carries. It becomes something the car is built from, and the implications are profound. Because the moment the battery starts carrying loads, you can remove entire layers of redundant structure. No more heavy protective enclosures, no more duplicated reinforcement, no more structure inside a structure. But there is a problem, a big one. Battery cells were never designed to do this. They were designed to store energy, not survive structural stress, not absorb crash loads, not handle torsional forces. So turning a battery into a structural component requires rethinking everything: materials, packaging, manufacturing. And this is where the first real breakthrough happened. Tesla's approach. When Tesla introduced its new generation platform, most people focused on one thing: the 4680 battery cell. A larger, cylindrical cell, more energy, fewer components. But that wasn't the real story. The real story was how those cells were used. Instead of placing cells into modules and modules into a pack, Tesla bonded thousands of cells together into a single rigid structure, using structural adhesives, creating something closer to a composite material than a battery pack. This block is then integrated directly into the vehicle, sandwiched between the front and rear sections of the car. And this is where everything changes, because now the battery is carrying structural loads. At the same time, Tesla introduced another radical innovation: Geiger casting. Instead of assembling hundreds of small metal components, they produce massive single-piece aluminum castings, one for the front, one for the rear, and the structural battery sits between them. The entire vehicle platform becomes just three major parts: front casting, rear casting, structural battery. What used to be hundreds of components becomes three. This is not optimization. This is simplification at an industrial scale. The Chinese approach. But Tesla is not alone. And in some ways, they are not even the most aggressive. In China, companies took a different path. Instead of focusing on manufacturing simplification, they focused on battery integration. This led to concepts like cell-to-body, cell-to-chassis. The idea is brutally efficient. Remove intermediate layers, eliminate modules, place cells directly into the vehicle structure. Companies like BYD developed the blade battery, long structural cells arranged across the floor of the vehicle, acting not just as energy storage, but as reinforcement. Meanwhile, CATL pushed even further, integrating the battery so deeply into the chassis that the distinction between battery and structure begins to disappear. At this point, the architecture itself is being rewritten. Why this matters? The advantages are not theoretical, they are immediate. First, weight reduction. By removing redundant structures, engineers can eliminate dozens, sometimes hundreds of kilograms. Second, increased rigidity. The battery spans the entire floor of the vehicle, acting like a massive structural panel, connecting the front and rear, reducing flex. Third, manufacturing simplicity. Fewer parts, fewer welds, fewer failure points, faster production, lower cost. And finally, efficiency. Not just at the battery level, but at the vehicle level. Because now, more of the car's mass is actually doing something useful, storing energy, carrying loads, instead of supporting redundant systems. This is where the story becomes undeniable. The battery is no longer just the heart of the electric vehicle. It is becoming its skeleton. And once that happens, the traditional chassis starts to look like an artifact. At this point, the technology is no longer theoretical. It is already dividing the industry. On one side are companies that are redesigning the car from the ground up. On the other are those still adapting old ideas to a new world. Take Tesla. Their approach is radical. They are not building electric cars. They are building entirely new architectures, structural batteries, gigacasting, three-part vehicle platforms. It is a clean break from the past. Meanwhile, companies like BYD and CATL are taking a different approach, less focused on manufacturing, more focused on integration. They control the battery supply chain, they control the chemistry, and now they are embedding that battery directly into the structure of the vehicle. Two strategies, same destination, and then there are the legacy manufacturers, companies like Volkswagen, Toyota, and Porsche. Their current electric platforms still follow a familiar pattern. The battery sits underneath the car, but remains separate from the structure. It is safer, more modular, easier to repair, but also less efficient, heavier, more complex. This creates a silent but critical divide between those designing cars around batteries and those still designing batteries around cars. And this leads to a question the industry can no longer avoid. Does this technology simply improve electric vehicles? Or does it change the rules entirely? Because if structural batteries become the standard, then everything the industry has learned about car design may need to be rewritten. For more than 100 years, the automobile has been defined by a single idea, a rigid chassis, carrying everything else. Every innovation, every breakthrough, every performance gain was built on top of that foundation. But the electric revolution has quietly rewritten the hierarchy, because in an electric vehicle, the most important component is no longer the engine, it is the battery. And now, that battery is beginning to take on a new role, not just as a source of energy, but as the structure itself. This is not a small improvement. It is a fundamental shift in how cars are designed, how they are built, and how they will evolve. In the future, cars may no longer be assembled around a frame. They may be assembled around energy, where the battery is not protected, but exposed as the core of the machine. And if that future becomes reality, then the chassis, the very backbone of the automobile, may become obsolete, not because it failed, but because something better took its place. And that raises one final question. If the battery becomes the car, then what exactly is left to redesign next?